Okay. So chapter 8 is on Laplace transforms. Section 4 involves the unit step function. So let me take a look and see what it is. Okay. All right, so 8.4, number 6. We have a function f of t, which is piecewise continuous, and it's defined to be t squared for t between 0 and 1, and 0 for t greater than or equal to 1. So from 0 to 1 is this parabola, but then there's a jump discontinuity, and it's equal to 1, it's equal to 0 for all t greater than or equal to 1. So we want to figure out, first of all, how to write this function as a linear combination of step functions. So we could try to write f of t. If we say it's t squared, well, that's what it is for t between 0 and 1. And for t greater than or equal to 1. So let me just also recall, what does the unit step function look like? So the unit step function is zero for t less than 0, and 1 for t greater than or equal to 0. And if we translate this by t naught, let's say this is t naught, this is the graph of the function u of t minus t naught, because when t is less than t naught, this is negative, so this is 0. And when t is greater than or equal to t naught, it's equal to 1. So here we have a jump when t is equal to 1. And so let's look at u of t minus 1. So when t is less than 1, this is 0. But when t is greater than or equal to 1, this is 1. And I really want to make this minus t squared, because, so what is this? If t is less than 1, this is 0, and the function is t squared. If t is greater than or equal to 1, this is 1, so I have t squared minus t squared is 0, or let me just write this as t squared minus u of t minus 1 times t squared. And the problem is to find the Laplace transform of f. So the Laplace transform of f, that's the Laplace transform of t squared minus u of t minus 1 t squared. By the linearity of the Laplace transform, that's the Laplace transform of t squared minus the Laplace transform of u of t minus 1 t squared. Now, the Laplace transform of t squared, we can recognize from the table, or you might just remember it. In general, the Laplace transform of t to the n is n factorial over s to the n plus 1. So this is equal to 2 factorial, which is 2 over s cubed. And what is the Laplace transform of u of t minus 1 t squared? So the Laplace transform of the unit step function times a function is, oops, let me just make sure I have this in the proper place. So let me just recall. So this was theorem 8.4.1, said that the Laplace transform of u of t minus tau g of t was equal to e to the minus s tau Laplace transform of g of t plus tau. So here, tau is equal to 1. And g of t is t squared. So this is 2 minus s cubed. When tau is equal to 1, this is e to the minus s times 1 times the Laplace transform. So my g of t is t squared. So g of t plus 1 is t plus 1 squared, which is t squared plus 2t plus 1. So this is the Laplace transform of t squared plus 2t plus 1. So this is 2 over s cubed minus e to the s. Laplace transform of t squared, again, is 2 over s cubed. Laplace transform of t, it's 2 times that, it's 2 over s squared. And the Laplace transform of 1 is 1 over s. So just being very careful with all of the basically high school algebra involved in this manipulation, that's the answer. Okay. Is there a question about that? Okay. And then someone asked, you asked about a question in problem 7. So let me get my book and look at chapter 7. So chapter 7, section 1, number 14. Okay. So that's a nice problem where we have to use a formal power series or a power series, or also called a Taylor series, to solve a second order differential equation. So let's take a look at that. So this is exercise . Which question did you have? section 7.1, number 14. And in this problem, we have the following differential equation: 1 plus x squared y double prime plus 2 minus x y prime plus 3y, and I assume what they mean is when it says find a power series solution y of x equals 0. So we have a second order linear ordinary differential equation with polynomial coefficients, and we want to find the solution y of the form summation a sub n x to the n, where n goes from 0 to infinity. So if y is summation a n x to the n, and goes from 0 to infinity, then y prime we can get by differentiating term by term. When you differentiate x to the n, you get n, x to the n minus 1. Or if, of course, this is 0 when n is 0. So this summation really starts with 1. And I can shift the index of summation. If I can replace n by n plus 1. This would be an plus 1, an plus 1 x to the n, where now n goes from 0 to infinity. Right? So for example, here, the first non-zero term when n is equal to 1 is 1a1. And here, when n is 0, you get 1a1. So that's okay. The second derivative you get by differentiating the first derivative. So this is summation, n goes from 0 to infinity, n, an. When you differentiate x to the n minus 1, you get n minus 1, x to the n minus 2. So this series really starts with n equal 2, because when n is 0, this is 0, and when n is 1, this is 0. So I can write this as a sum from 0 to infinity. I replace n by n plus 2. I get n plus 2, n plus 1, an plus 2, x to the n. So this is my power series y. I have two expressions for y prime, and I have two expressions for y double prime, but of course they're equal. So let's plug this into the differential equation and try to calculate these coefficients of the power series, the a sub n's. So 1 plus x squared y double prime plus 2 minus x y prime plus 3y. Let me just expand this. This is y double prime plus x squared y double prime plus 2y prime minus xy prime plus 3y. So y double prime, I want to have all my series going from x to the n, x to the n. So this is y double prime. This is summation, n goes from 0 to infinity, n plus 2, n plus 1, an plus 2, x to the n, plus x squared y double prime. So when I write this, I'm going to use this expression for y double prime, because when I multiply this by x squared times x to the n minus 2 is x to the n. So I get summation, n goes from 0 to infinity, n minus 1 a sub n, x to the n. Right? I'm multiplying y double prime by x squared. That makes this x to the n. Then 2y prime, here's y prime, plus summation, n goes from 0 to infinity, 2 times this, 2 sorry, I'm going to use this expression. So 2y prime, that's 2 n plus 1 an plus 1 x to the n, minus xy prime. Now, if I take this expression for y prime and multiply by x times x to the n minus 1 is x to the n. So this is minus summation n goes from 0 to infinity, n an x to the n, plus 3y plus 3y. So this is just summation 3an x to the n goes from 0 to infinity. So in this differential equation, I have 5 terms. And when I expand it and plug in the power series, I get 1, 2, 3, 4, 5. I get 5 power series, but I can collect the terms. This is summation, n goes from 0 to infinity. So I'm going to have something times x to the n. What is the coefficient of x to the n? I have n plus 2, n plus 1, an plus 2, plus n minus 1, an, plus 2, n plus 1, an plus 1, minus nan plus 3an. And all of this has to be 0, which means every one of these coefficients of x to the n has to be 0. So let's write that coefficient down and just do a little bit of high school algebra to simplify the terms. So 0 is going to be equal to, this is n plus 2, n plus 1, an plus 2. And then I have plus 2, n plus 1, an plus 1. And then I have an. I have n minus 1 an minus nan minus n plus 3 an. So I have n plus 2, n plus 1, an plus 2, plus 2, n plus 1, an plus 1. And an is multiplied by n times n minus 1 minus n plus 3. So this is n squared minus 2n plus 3. So in the unlikely event that my algebra is correct, the an's, the numbers an satisfy this recursion relation. And we have to solve that. Oh, actually, so we don't have to solve that. So this is all we have to do for this problem. It just wants us to find a recursion relation, or the condition that the coefficients of the power series have to satisfy. It's n plus 2, n plus 1, an plus 2, plus 2n plus 1, an plus 1, plus n squared minus 2n plus 3, a sub n. So that's all we need to do. So that's all we're being asked to do in this problem. So if you start with this expression, this is why they didn't write equals 0. If you start with this expression, 1 plus x squared y double prime plus 2 minus x y prime plus 3y, and you plug in a power series, what you get when you collect the terms is a power series, exactly this power series, which when you, and this term, right, exactly that power series, where the nth term is this plus this, the coefficient of x to the n is this. And we get a little bit of algebraic simplification, and we get that. In any case, that's what we're asked, that's all we're asked to do in this problem. Anything else we can do? So section 7.2, exercise 16. So here we have the differential equation y double prime minus y equals 0, but we want a solution y which is centered around the point x naught equal 3. So summation x minus 3 to the n goes from 0 to infinity. So we want to find a power series in x minus 3. Oops, let me get this out of the way. So this is what we're doing. Section 7.2, exercise 16. We have the differential equation y double prime minus y equals 0, and we want to find a power series in x minus 3 that solves this equation. Of course, we know for this differential equation, the general solution is the cosine and the sine, but we want to find the solution with a power series centered at 3 and not centered at 0. So the algebraic manipulations are always the same. This is y. So y prime is summation n x minus 3 to the n minus 1, and goes from 0 to infinity. That's the first derivative. And the second derivative is you just differentiate this again. Summation n goes from 0 to infinity, n minus 1 x minus 3 to the n minus 2. Right? When you differentiate x minus 3 to the n minus 1, you get n minus 1, x minus 3 to the n minus 2. And if we want to shift this summation, if I replace n by n plus 2, I get n plus 2, n plus 1, n plus 2, x minus 3 to the n goes from 0 to infinity. So y double prime minus y, here's y double prime, summation n goes from 0 to infinity, n plus 2, n plus 1, n plus 2, x minus 3 to the n, minus y, so I'm subtracting for each term n x minus 3 to the n minus n x minus 3. And that has to equal 0. Which means n plus 2, n plus 1, n plus 2 minus n equals 0 for all n. So this is a recursion that I can solve, and you get different sequences for even and odd numbers n. So a0 is whatever a0 is. If we let n equal to 0, we get 2 times 1, a2 minus an equals 0, or equals a0. So a2 is 1 over 2 times 1, a0. If you let n equal 2, you get 4 times 3, a4. I can just write this as equals an, equals a2. So a4 is 1 over 3 times 4 times a2, but a2 is 2 times 1, or I just may write this as 1 times 2, is 1 times 2 times 3 times 4 a0, which is 1 over 4 factorial a0. This is 1 over 2 factorial a0. And if you look at this, you start to see what you think will be a pattern. So if a sub 2n is equal to 1 over 2n factorial a0, then in this recursion, if you let n equal 2n, you get 2n plus 2 times 2n plus 1, a sub 2n plus 2 equals a sub 2n, which is 1 over 2n factorial a0. So a sub 2n plus 2 is equal to 1 over 2n factorial times 2n plus 1 times 2n plus 2, a0, that's 1 over 2n plus 2 factorial a0. So what we conclude is that a sub 2n is 1 over 2n factorial a0 for all n. So this gives us the even coefficients. What about for the odd case? So again, we have the recursion n plus 2, n plus 1, an plus 2 minus an equals 0, which is the same as saying that an plus 2 is 1 over n plus 1, n plus 2, an, and that's true for all n. So for example, if you let n equal to 1, you get a3 is equal to 1 over 2 times 3 a1, which is 1 over 3 factorial a1. If you let n equal to 3, you get a5 is 1 over 4 times 5 times 3 factorial. Sorry, 1 over 4 times 5 times a3, which is 1 over 4 times 5 times 3 factorial a1, or 1 over 5 factorial a1. And in general, you will see that a2n plus 1 is 1 over 2n plus 1 factorial a1. So what we see, in fact, is for all n, an is 1, even or odd, is 1 over n factor. So not for all n. A2n is 1 over 2n factorial a0, and a2n plus 1 for odd numbers, we get 1 over 2n plus 1 factorial a1. So the general solution of this differential equation, y double prime minus y prime equals 0, we get summation an x minus 3 to the n goes from 0 to infinity. It depends on whether n is even or odd. So this is equal to summation over all the even n even, a0 times, I can write this as a sub 2n x minus 3 to the 2n. And for n odd, I have a1, and this an, this is over 2n factorial, and a1 summation x minus 3 to the 2n plus 1 over 2n plus 1 factorial. So this is, n goes from 0 to infinity, and goes from 1 to infinity. So this is the power series solution of this differential equation around x minus 3.
Thank you, Professor.
Okay,
Can you go over 8.3, question 7?
okay, let's see. So let's get some clean paper to write on. Section 8.3, exercise 7. Let me turn to chapter 8. Eight point three. Exercise 7. So we want to use the Laplace transform to solve the differential equation y double prime plus y equals the sine of 2t with the initial conditions that y of 0 equals 0 and y prime of 0 equals 1. So if y is a solution, suppose we let y of s be the Laplace transform of y. So the Laplace transform of the left-hand side of our equation, y double prime plus y, is the Laplace transform of y double prime plus the Laplace transform of y. The Laplace transform of the second derivative of y is s squared times the Laplace transform of y minus y prime at 0 minus s times y of 0. So this is s squared times y, Laplace transform of y. Plus the Laplace transform of y, plus y. So we've s squared y minus y prime of 0, which is 1, minus s times y of 0, which is 0, plus y. So that's s squared plus 1 times y minus 1. And this is all equal to the Laplace transform of the sine of 2t. So if we look at our table of Laplace transforms, we have sine of omega t. So when omega is equal to 2, this is 2 over s squared plus 2 squared, or 4. So we have s squared plus 1 y minus 1 equals 2 over s squared plus 4. So s squared plus 1 y is 1 plus 2 over s squared plus 4, or y is equal to 1 over s squared plus 1 plus 2 over s squared plus 1 times s squared plus 4. So this is the Laplace transform of my solution, little y. So I want to find y, which is the inverse Laplace transform of 1 over s squared plus 1 plus 2 over s squared plus 1 s squared plus 4. And So the inverse Laplace transform of 1 over s squared plus 1, we can recognize as simply the sine of t. And for this, we might want to expand this in partial fractions. So let's see. So this expression, 2 over s squared plus 1 times s squared plus 4, this might be equal to 2 over s squared plus 4. Let's see. I'm just going to see if I can do it without doing too much algebra. Let's see. If I'm lucky, this will be like a over s squared plus 4 plus b over s squared plus 2. So I'll put a question mark next to that. If that's the case, that means that if I cross multiply, 2 is equal to a times s squared plus 1 plus b times s squared plus 4. And if I want to solve this, this means that a plus b is 0. So this is a plus b s squared plus a plus 4b equals 2. So this has to be 0, and this has to be 2. This says that a is minus b. So this would say that a equals minus b, and 3b is equal to 2. So b is 2/3 and a is minus 2/3. Let's see. Let me just see if this might be actually correct. So if I take 2/3, 1 over s squared plus 1, minus 2/3, 1 over s squared plus 4, that's equal to s squared plus 4 minus s squared plus 1. Yeah, that's actually correct. So it's my lucky day. What this says is that, let me come back to this. Y is this inverse Laplace transform. Let me just copy that down again so everyone can see it. Y is the inverse Laplace transform of 1 over s squared plus 1 plus the inverse Laplace transform of 2 over s squared plus 1 s squared plus 4. And this is the inverse Laplace transform of 1 over s squared plus 1 plus the inverse Laplace transform. We just saw this is 2/3 1 over s squared plus 1 minus 2/3 1 over s squared plus 4. So I have the inverse Laplace transform of 1 over s squared plus 1 plus 2/3 times 1 over s squared plus 1. That's 1 plus 2/3 is 5/3, inverse Laplace transform of 1 over s squared plus 1 minus 2/3, the inverse Laplace transform of 1 over s squared plus 4. Now, the inverse Laplace transform of 2 over s squared plus 4, let me make this 1 and this 2. So this is 5/3. The inverse Laplace transform of 1 over sine squared plus 1 is sine t. minus a third. This is the inverse Laplace transform of sine of 2t. So if I am lucky today, exercise 8.3 is problem number 7. 5/3 sine t, minus 1/3 sine 2t. So that's what my solution using the Laplace transform says, but we have to know this is correct. So the only way you know if a solution is correct is if you check. So this is y. What is y prime? Y prime is 5/3 cosine t minus 2/3 cosine 2t, and y double prime is minus 5/3 sine t plus 4/3 sine 2t. So if I take y plus y double prime, this plus this term cancels. 4/3 minus 1/3 is 1/3. This is sine 2t. So this does satisfy my differential equation. And y of 0, when t is 0, this is 0. Y prime of 0, when t is 0, this is 5/3 minus 2/3, which is 1. So everything checks, and it's my lucky day. Got it right. Okay. Other questions? So section 8.3, exercise 5. So let me turn to that in the book. So 8.3, section 5, so 8.3, problem 5, is to solve the differential equation y double prime plus y prime minus 2y equals e to the 3t, with the initial conditions that y of 0 is 1 and y prime of 0 is minus 1. So that's our problem. So again, we're going to take, so we're told to use the method of Laplace transforms to solve this problem. And you always have to make sure you have your table of Laplace transforms handy. So the Laplace transform of y double prime minus y prime minus 2y. So suppose we let capital Y be the Laplace transform of the solution. So this is the Laplace transform of y double prime minus the Laplace transform of y prime minus 2 times the Laplace transform of y. So the Laplace transform of y double prime is s squared y minus y prime of 0 minus s y of 0. Right, that's the Laplace transform of the second derivative. Minus the Laplace transform of y prime, which is s times the Laplace transform of y minus y of 0 plus 2 times the Laplace transform of y. So this is s squared minus s plus 2 times y minus y prime of 0, that's minus 1, minus s times y to 0 minus s, plus y of 0, which is plus 1. And that's all supposed to equal the Laplace transform of e to the 3t. And the Laplace transform of e to the 3t is 1 over s minus 3. So if I've done my arithmetic correctly, s squared minus s plus 2 times y is equal to, this is 2 minus s, so it's s minus 2 plus 1 over s minus 3. So let me just double check that I did my arithmetic correctly. So the Laplace transform of y double prime is s squared Laplace transform of y minus the derivative at 0 minus s times the value at 0. And the Laplace oh, here's a mistake. This is a plus. Plus the Laplace transform of y prime, which is s times the Laplace transform of y minus y of 0 minus, I don't know why I got these time, minus 2 times y, minus 2 times the Laplace transform of y. So that's equal to s squared plus s minus 2. Always good to do arithmetic correctly. S squared plus s minus 2 times y.
Professor, can you move the paper up?
Oh, sorry. Yes. So it's s squared plus s minus 2 times capital Y minus y prime of 0, which is minus 1 is plus 1, minus s times 1 is minus s, minus y of 0 is minus 1, equals the Laplace transform of e to the 3t, which was 1 over s minus 3. So this is not, so this is just minus s. So when I bring this over to the other side, I have s plus one over s minus 3. And this is s squared plus s minus 2, which is the same as s plus 2, s minus 1 times y equals this. So y is equal to s over s plus 2, s plus 1, plus 1 over s plus 2, s minus 1, s minus 3. So the Laplace transform, oops, what is this? The Laplace transform of y is equal to this expression. Oops, s plus 2, let me write this correctly, s plus 2, s minus 1, plus s plus 2, s minus 1, s minus 3. So what I want to do is expand this in partial fractions. Maybe just I'll put this over a common denominator. This is s minus 3, s minus 3. So this is over s plus 2, s minus 1, s minus 3, and in the numerator, I have s squared minus 3s plus 1. If my arithmetic is correct, that's what this is equal to. And this should be written as partial fractions, a over s plus 2 plus b over s minus 1 plus c over s minus 3. And I need to solve this equation for a, b, and c. So I believe, for example, if I multiply by s minus 1 and let s equal 1, I would get b equal to 1 plus 1 minus 3 minus 1 over 3 times minus 2. I would get, I think, b equal to a sixth, and so on. In any case, this is now just algebra. You just solve this, you write this in partial fractions, you get an expression that looks like this. And so y, which is the inverse Laplace transform of this capital Y, is the inverse Laplace transform of these three expressions. And each of these is an exponential. This will be equal to a times e to the minus 2t plus b times e to the t. Sorry. This is b times e to the t, c e to the 3t, and for 1 over s plus 2, what is that? Yeah. So a times e to the minus 2t, b times e to the t, c times e to the 3t. So b is equal to a sixth. If I want to calculate a and b, if I multiply through by s plus 2, I would get a equal to, when s is minus 2, you get 4, 10, you get 11 over minus 3 times minus 5, minus 50 over 15. And anyway, in any case, you can calculate those numbers. That's just high school algebra.
Professor, can you move the paper? Thank you.
Yeah. But this is, I mean, this expression you'll write as partial fractions, a over s plus 2, b over s minus 1, c over s minus 3. So with these numbers, a, b, and c, which you can calculate, the solution of this differential equation is this linear combination of e to the minus 2t, e to the plus t, and e to the plus 3t.
Thank you, Professor.
Okay. All right, if there's nothing else, that's fine. Again, Monday, Wednesday, and Friday, I have problem sessions. I think 1 o'clock today, 1 o'clock on Wednesday, 11 o'clock Friday morning. But I'm also available Tuesday and Thursday if you need, and you can just email me and we can set up a time.
Okay, then I'm definitely going to email you for tomorrow.
Okay, very good. Okay. All right, be well all. Bye.
Bye.